x-axis. All right, next sheet, 2 more to go, all right? The next one, a hyperboloid of 1 sheet. It looks kind of like a cooling tower for a nuclear plant. Maybe, I don't know. But it looks like something, right? So look at the equation. Yes?
1 sheet, what do you mean?
Well, you have to see what the next one is, which is the same thing of 2 sheets. Look at the equation. Damn, look, if that was a plus, it would be an ellipsoid, right? But it's a minus on the z term, and so it looks like that. Do y'all see that that kind of goes up through the z-axis? And the z is the thing that's being subtracted. Let me change the equation. X squared, z squared, those are being added. Subtract the y squared equals 1, and you get that.
What's this called again?
A hyperboloid of 1 sheet. Hyperboloid of 1 sheet. And then the last kind of possibility is where you've got the x squared as the one being subtracted, and that would go down your x-axis. So let me actually change some numbers here. Watch, if I start changing the numbers, I change the shape. All I'm doing here is I'm changing the A, the B, and the C. I start changing this shape. If you change things enough, what will happen is you'll pinch it off in the middle, and it'll separate into 2 pieces. And that's the hyperboloid of 2 sheets, and that's this picture. Right? So if it's like this picture, imagine just kind of coming in here and kind of squeezing it together, and eventually it breaks off into 2 little blobs, and you get that. And there's the equation of it.
Oh.
You see now what we have? All 3 variables, all of them squared, equals 1. 2 of them are negative, 1's positive. 2 negative, 1 positive. The other one, it was 2 positive, 1 negative, right? All right, there they all are. Let me actually do an example, all right, of something that I would want you to be able to do. So I'm going to start with this one here. Let me just make some room for myself. All right, here's what I want us to do. Take that equation, reduce it into standard form, and identify basically and classify what it is we're looking at. So I want to take that equation, I want to make it look like one of the standard forms that we just looked at, and then see if I can somehow classify this. Like, what is it? Is this an ellipsoid? Is this a blah, blah, blah? So I look at this. I have what x, y, and z are all there, right? They're all squared. Right? They're all squared. 2 of them are on one side being added. The other one is by itself. Let me scroll back up and see if we can find that. 2 variables by themselves squared being added.
There.
Is that it? Was the other side squared?
Yeah.
Yeah? Does this look like it to everyone? What was that? Cone? Right. 2 of the variables being added squared. Okay, so it should be a cone, right? But I've got to make it look like this, or like this, or like this. Let me go back to the problem. Where the heck is it? There we go. So I can't have a 2 here, so watch what I do. This is just me being clever. I'm not saying I'm clever, just saying I'm going to do something clever. I'm going to rewrite that like this. That's the same thing, isn't it? 2 in front is the same as dividing by a half. See, what I'm trying to do is make it look like this. X squared over a squared equals y squared over b squared plus z squared over c squared. See, I'm trying to make it look like this. And then this side would be over 1, right? And so now what I could do is those things on the bottom need to be something squared. So I'm going to write this as x squared over, well, 1 is 1 squared. This is y squared over, to rewrite 1/2 as something squared, I'm going to put the square root of 1/2 squared. So the square root of 1/2 squared plus z squared over the square root of 1/3 squared. That is the standard form of that cone. So I'm going to say here this is a cone, right? This is a cone. Looks like this. And so A for me is 1, B for me is the root of 1/2, and C for me is the root of 1/3. And going back and looking at the notes, you'll see that whatever variable is by itself, right, not the ones being added together, the one that's by itself indicates the axis that the cone goes down. So if I were to actually draw this, rough sketch of this, I know that it goes like this, roughly, down the x-axis. I didn't ask for a sketch, but that's just me realizing what it kind of looks like. Yes?
Would you just be able to divide by 6?
Pardon me?
Would you be able to divide by 6 on both sides?
Divide by 6 on both sides.
And 2 and 3, then you just square root the denominators.
Yeah, that's just a scalar multiple of this equation.
Oh, okay.
Yeah. You can multiply both sides. It's just a different way that would be a different way of getting the same thing. All right, let's do the next one. Were there any questions on that one? Everyone see how I did that? All right, let's see here. Same thing, we want to kind of look at this, classify it, see if we can't figure out like the general look of this thing. So I see all 3 variables, right? X, Y, and Z are here. Let me list it out on this side. I realize this section is really like dry and blah. The next section is going to be a little more exciting. We have X, Y, and Z, right? All 3 variables. Let's see, 2 of them are squared, right? The Y and the Z are squared, and the X, right, is linear, you could say, because it's not squared. So let me just process of elimination here. Let's see if we can figure out what it can be. All right, I'm going to scroll all the way up to the top of this. All right, can it be our first one? Can it be a cylinder? No, because all 3 variables are squared here. So it can't be a cylinder. Can it be a parabolic cylinder? Why? Yeah, because for these have 1 free variable, and our equation has all 3 variables in it. So it can't be that. Okay. Can it be an ellipsoid? All 3 are there, right? Are they all squared?
No.
Here they are, here they aren't, right? So it can't be that. Y'all see what I'm doing? I'm just kind of eliminating things. Did I go too fast there? Yeah. Elliptic paraboloid is next. And this one has 2 variables are squared, the other one's not, right? That's looking somewhat promising. So what is this? What is this again? This is the elliptic paraboloid. Elliptic paraboloid. I'm just going to maybe it's an elliptic paraboloid. Let's see the next thing. Elliptic paraboloid. Still an elliptic paraboloid. Okay. Hyperboloid or hyperbolic paraboloid. Do I have 2 variables? All 3 variables are here. 2 of them are squared, one's not, right? Yeah. Could be this. This is a hyperbolic paraboloid. So it could be a hyperbolic paraboloid, right? Don't know yet. Cone. No, right? All 3 variables are squared. Can't be that. Can't be this, right? Hyperboloid 1 sheet, all 3 variables are squared. Can't be this. And it can't be the hyperboloid 2 sheets because all 3 variables are squared. So it's either an ellipse or a hyperbolic paraboloid. Got it? Yep. All right, now what I'm going to do is I'm going to go to this one. This one might be a little bit easier. This is the one that's out of the book. But I need to write the equation down. What? Ooh, wrong one. Let me write the equation down. So 4x minus y squared plus 3z squared equals 0. All right, that's what I'm working with there. And bringing up that sheet from here. Ooh, look at that. We said it could be a hyperbolic paraboloid, right? Look at this. I've got two of the variables together squared, right? And there's a subtraction symbol between the two. And then the other one would be on the other side positive. I'm thinking it's probably this because I can rearrange, can't I? Let me try and get an empty spot here. So here, let me leave the 4x on this side equals, let's move these two to the other side so you get y squared minus 3z squared. Do you see I'm trying to get it to look kind of like this?
Yeah.
But I'm not really dealing, I don't care about z, x, and y. I just care about like the general pattern. Variable equals variable squared minus variable squared. That's what I'm shooting for. And then next I'm going to do that same thing I just did a second ago. I'm going to rewrite this as x over 1/4, and then equals y squared over 1, and then minus z squared over 1/3. See, I'm trying to get it closer and closer to this, right? And then I just need to look at these two as these two as something squared. So I think my last line here, I'll have x over 1/4 equals y squared over 1 squared minus z squared over the square root of 1/3 squared. There we go. That would be the standard form for that. What is this thing? A what? A hyperbolic paraboloid. Why is it not an elliptic paraboloid? Maybe we should go back. What's that? Because there's an, where? On, oh, there's a negative here.
Yeah.
Yes, there's subtraction between the two variables. And that would be impossible to get rid of, right? On the squared variables, one of them's negative, the other one's positive. There's no way to change that. So it's always going to maintain that relationship. So it's got to be the hyperbolic paraboloid. That's what I expect that you can do. Does that seem fair? There's one more thing that you should be able to do. I think it's the last one here. Yeah, this is the hardest one. Yeah. Yeah. So you look at that and you're like, shit, I must have missed that part of the lecture. Do we have all three variables?
Yes.
Okay, so all three variables are here. That eliminates some things, right? That eliminates some things already because some of the equations we had only had, you know, two of the variables. So all three are there. Do I have all three squared? Yes. So they're all squared. That eliminates some as well, right? But there's still a slew of things it could be. Let me bring up the sheet out of the book so we can see how. So could it be this one? Do we have all three variables squared in there? Yeah, so it could be an ellipsoid. Could it be an elliptic paraboloid? No. Could it be a hyperbolic paraboloid? No. Cone? Maybe, right? All three variables squared. Could it be a hyperboloid one sheet? Possibly, right? All three variables squared. Could it be hyperboloid of two sheets? All three variables squared. I got to figure out which of those it is. All right, so back to the problem. What's that?
Can you actually go back
Yeah. Where? To the.
to the previous one with the shapes?
Yeah.
To the, I think it's up to. Can't it not be a cone since there's a coefficient? Or not a coefficient, a constant?
A constant.
A constant in the original one?
Oh, in the original one.
In the cone. There's no constant in the cone. So
Well,
it can't be that.
okay, I see what you're saying. So what's being pointed out is that this doesn't have a constant in it, right? And here we actually do have a constant. Y'all see that? That would normally, I would agree with you if this, and this didn't appear. If these three terms weren't here, I would agree, because you'd have variables squared, you'd have a constant. And then it couldn't be, right? But these are here, right? So any ideas on what we're going to have to do? Yes. Complete the square. We're going to have to complete the square. So all of the objects that I've shown you, let me go back and formulate this idea this way. This right here is a sphere, right? Sphere with a radius of r. Right? That's a sphere of radius r. This is a sphere of radius r where I've changed the center, haven't I? I've moved it. Every single thing we've looked at today, all of these different things, you can shift them to a different kind of central point. And you do it by adapting the formulas. So like this formula right here, you could rewrite this as like z minus L squared over c squared equals x minus h squared over a squared, and then plus y minus k squared over b squared. Understand? And it would just move it, it would move this cone, you know, wherever you want it, right? So when we complete our square here on this problem, we're going to basically, whatever this winds up being, it's going to have been shifted. It's going to have been moved somewhere. So let's complete the square. And then we'll classify it and write it in standard form, and then we'll be done. We'll be ready to move to the next section. So I'm going to just rewrite x squared minus 2x minus y squared plus 2y plus z squared plus 4z plus 2 equals 0. Okay. So I collected my x terms together, my y's together, my z's together. All right, I'm going to complete the square on each of these. So to complete the square on the first one, I'm going to take half of that number. Half of negative 2 is negative 1. I'm going to square it, which is 1. And now I'm going to add it and subtract it. So I'm going to add a 1, subtract a 1. All right, on these two terms, I cannot complete the square yet because I have a negative coefficient on the y squared. So I have to pull a negative first out. And I'm just going to pull that negative out of these two terms. All right? And then here, I'm going to go ahead and complete the square because I don't need to pull a negative out. I take half of 4, which is 2. I square it. I get 4. I add it and subtract it. And then I still had plus 2 equals 0. Any questions there on what I've done? Sure? Let me complete the square on this one right now. I'm going to rewrite the whole line. I realize I could simplify it, but I'm just going to rewrite everything. Okay, negative. All right, in this parentheses, I take half of negative 2. I'm sorry, yeah, half of negative 2, which is negative 1. I square it, which is 1. I add and subtract it. So y squared minus 2y. I add and subtract a 1 right there. And then plus z squared plus 4z plus 4 minus 4 plus 2. Do you see what I'm saying, sir? What was your name again?
Nick.
Nick?
Yeah.
Okay, Nick. Do you see what I'm saying? How when we complete the square, there is a possibility that that could go away. Like these numbers that I add and subtract could wind up killing that constant off, and then it may not be what we thought. So you have to be careful with that. All right. Let me complete this now. These first 3 terms will factor. These 3 terms will factor. These 3 terms will factor, guaranteed. So we'll have x minus 1 squared. That's the perfect square trinomial, right? Then I have minus 1 here still. Then a minus, parentheses. These 3 terms become x minus 1, that quantity squared. Still have a minus 1, still in a parenthesis. And then down here, z plus 2, that quantity squared, still have a minus 4 and a plus 2 equals 0. I'm getting there. X minus 1 squared minus 1 minus the quantity y minus 1 squared plus 1. So there, all I did was distributed the negative and threw it in front of this, which made that, and then put that negative in here and got the plus 1. And then I just continue writing everything, and I'm almost there. Well, not really. I still have more work to do. Minus 4 plus 2 equals 0. Yeah, some stuff goes away here, huh? So I get that goes away, negative 2 here, right? All right, let me write the next line. Okay. All right, so I have equals x minus 1, that quantity squared. Then I have minus y minus 1, that quantity squared. Then I have plus the z plus 2, that quantity squared, and then equals 2. Sorry, well, I don't know why I wrote equals here. Right? Hold on a second. I had an equals in front. Take those equals out of there. I was working with an equation the whole time. I don't know why I had an equals out front. It's more like this line goes to the next line, to the next line. Sorry, I was carrying my equals. That's a mistake on my part.
That's a mistake.
Yeah, because if I write this equation down, right? And then let's say I add 1 to both sides, okay? I wouldn't say equals x plus 5 equals 3. Because then it starts looking like you're trying to say that that's equal to 2, which is equal to that, which is equal to 3. It looks more like a string of equalities, and that's not right. You do this, and now it's one line to the next. From here to here, you added 1 on both sides. All right. I already knew I had all my variables squared, right? I already knew that. I have 2 of them are positive, subtraction, but I have this 2 over here, right? What do y'all think? Divide both sides by 2? Yes?
Oh, sorry, I'm just lost. Can you explain again how you got a constant of 2? Because, like, when you're completing the square and you add and subtract, I lost track of my constants. Was it for the y term, it was plus 1 minus 1?
Plus 1 minus 1. So the plus 1 went together in here. So the line above this was negative, parenthesis, it was y squared minus 2y, right? And we added 1 and subtracted 1. That's what we had in parentheses.
Yes.
And then these 3 became that. And then that minus 1 came here, right? But remember, we had a negative in front of everything, right? So that negative has to go in front of this squared term. And then the negative and negative become the plus right there.
Oh, the negative applies to that one as well.
That's right. That's right. Yeah. So that's why that putting the negative in front of the variable like that is tricky, because you can lose track of that. So it's important to keep this all in parentheses when you complete that square. Uh-huh. All right. What do we have here? Going back to all of our options. Let's divide through by 2. If I divide through by 2, I get 2 here, 2 here, 2 here, and 1, right? Do we have anything that looks like that? Do we have anything that has all 3 variables equal to 1? And there's subtraction between one of them.
We could also.
Not quite this, right? Not quite this. Not that. Hold on a second. Ah, there we go. Look at that. All 3 variables are squared, right? 2 of them have a positive. 1 of them is negative, equals 1. That's what I have here.
Right.
Y'all see it? Now, does it matter that these are all the same numbers down here? No, that doesn't. That's okay. All right, that's okay. So there it is. Oh, what was that? We didn't say what that was.
I
That was a hyperboloid of one sheet. Hey, let's graph this, because we said that, you know, the whole idea here is that we have technology, right? So I'm going to go to GeoGebra, which is a graphing utility. It's not as good, in my opinion, as Desmos for two-dimensional graphing, but you can also do three-dimensional graphing here. So I'm going to try this. I don't know, I've never put this in here before. Well, I haven't done it in a long time. So we got x minus 1, that quantity squared, divided by 2, plus, minus y minus 1, that quantity squared, divided by 2, plus z plus 2, that quantity squared, divided by 2 equals 1. There it is.
Watching the process of that gave me anxiety.
Yeah, seeing it like it's trying to adapt to what I'm typing in, right? Can y'all see that that is the hyperboloid of one sheet? I mean, the picture, the image I have of it, or that we have of it, is a little bit different, but yeah, it is what it is.
So it's
Yes.
factored at 1, 1, -2.
Yeah, it's hard to see that here, but let's go look at it. Lauren, did you have a question?
I did. When writing a standard form, would you want to do the same thing you did before and put the squares?
Yeah, you could write this as square root of 2 squared, square root of 2 squared, square root of 2 squared.
Would you accept that, though?
If I said find like A, B, and C, then I would need the square root of 2. But in standard form, this would be okay. For the same reason that when you write like the equation of a circle, no one says you have to write 3 squared there, right? It's understood that the radius is 3. Yes?
So when we were looking at the formulas in the beginning, trying to figure out what kind of shape it could be, couldn't we have eliminated some of those formulas?
Oh, yeah.
Because of the fact that y squared was negative?
No, because there are some like this one. If you move the z squared to the other side, it's negative, right? Like just make this whole term, put it on that side. It would be 0 equals that, right? And then you would have the negative z squared term on the other side. Are you following me?
Yeah.
So, no, you have to be careful with it, especially if you have to complete the square. Okay, so the question, was it centered? So it's centered, this would be centered at 1, 1, -2. Now, I don't know. Let me see if I can graph that point. Whoa, oh shit, look at that. It's spinning itself. I'll just let it keep doing that. It's kind of cool. I'm going to go to 1, 1, -2. Do y'all see it there?
Yep.
Right? There's kind of like, if there is a center, if we can talk about center of this thing, that's where it is. Let's look at it from the top. Right. So if we're looking at it, right? So if you go out 1 on the x-axis, 1 on the y-axis, 1, 1, and then -2, that means we're down into the z, right? So let me rotate this. See it? Out 1, over 1, down 1. Or down 2, sorry. All right, y'all got it? All right, we're done. Let's put this section to sleep.
You sure we can't stay in the same?
Yeah, I can't stand this section. This is one of my least favorite sections, probably the least favorite sections to do in this class. Because we're just looking at stuff. It's not really.
Well, it's great. We're just
Yeah,
looking.
we're just looking. Yeah, let's bring popcorn and.
Yeah,
Third is this course, calculus.
All right, this next section, 10.7, really, really big section. I think there's 16 notes and 16 examples in this section. There's a lot of material here. So we're going to get through as much as we can today, but there's no way we finish it, all right? So now we begin to talk about vector functions. And I want to talk a little bit more abstractly first about functions. So functions that you've studied so far, example, f of x equals x squared. We could write this way. F goes from R into R. So what this function does is it takes a real number, right? Does something to it, spits out another real number. Real number in, real number out, right? And that's pretty much what we've studied. All of Cal 1, all of Cal 2, that was what we did, right? What we're going to be looking at now are functions that don't do this, all right? We're going to be looking at a function, but we're going to call it R. And this function is actually going to take in a number, and it's going to spit out either a two-dimensional vector, or it's going to take a number in and spit out a three-dimensional vector. All right? So it goes from R, this would be R2 or R3. See? Number gets sent to a number from like linear space into linear space. To visualize this, right, to see this picture, you need an x-axis and a y-axis, right? Here, if I take in a number and spit out a vector, I need one dimension for the input and 2 dimensions for the output, which means I need 3-dimensional space to visualize, right? Or here, one dimension for the input and 3 for the output, so that's 4 dimensions. That's going to be hard for us to do, right? All right, but I just want you to see the main idea. Everything we've studied, number goes to number, right? Number goes to number. Now we go number goes to vector. So that's what the beginning of these notes start to address. All right, a vector function, a function, R with the little arrow on top, R of t, that's what lets you know it's a vector function as opposed to like f of x or f of t, which is what we call a scalar function. This is a vector function. What it does is it takes some input t. That t is a number. And it creates a 2-dimensional vector. Or it could create a 3-dimensional vector. The first part of the vector is some function we call f of t. The second one is g of t. Those two functions, f and g, or in the case that we have 3-dimensional vector, h of t, those 3 individual functions are just regular functions like that we've studied our whole lives, all right? This is called a vector function or a vector valued function. That's the definition of it. All right, vector functions, the domain, this is what I was just saying, domain, it takes in numbers, it spits out vectors in either 2 or 3-dimensional space. Given a vector function, these functions, f and g,